Hello, welcome to my presentation about traveling repair person problem, unrelated machines scheduling, and other similar problems. This is the joint work with Marcin and Alison. So let's start with the definition of the traveling repair person problem. In the beginning, we are given some metric space that is a city in this case. So this consists of houses, and we've got some plumber that lives in one of the houses, and he has his own car. Then there was some accident that some pipes got broken at one moment in time, so they started leaking. The goal is for the plumber is to repair all of them. What we know about the plumber? We know that he is very fast in repairing everything. He is repairing everything immediately. However, his car has limited speed. So while he's driving, the water is leaking from the pipes. So let's take a look into an example. Here we've got the plumber, and for example, he can go at first to this pipe. He can solve this problem, and the cost of servicing is just the amount of water that got out from this pipe. And then he is going to the next broken pipe. However, this problem is online, so it means that we don't have the full knowledge about the instance in the beginning, and some information about broken pipes may appear later. So, for example, in this moment, we can observe that there are 3 broken pipes in this house. And we couldn't repair them before because we didn't know about them. So the plumber now needs to decide where he wants to go. Or he wants to go to this house and repair all these pipes, or to these houses. So for example, he can go to this house, repair all these 3 pipes at once, and he's paying for every of them separately. Then he is going to this house, repairing the pipe and repairing the last pipe. And here we can observe that this is the total cost of the algorithm here. Our goal is very natural, so we want to minimize the amount of water that got out from the pipes. And as the problem is online, we want to minimize the competitive ratio of the algorithm. That is the ratio of the algorithm over optimal solution for the worst possible instance that can appear in this problem. As the previous results, here we can observe what were the ratios before for the deterministic and randomized case, and what are the lower bounds for these problems. And I will present you an algorithm that achieves a competitive ratio of 4 for deterministic case and competitive ratio of 2.8 for randomized case. What can I say about these problems, these algorithms? Okay, these previous algorithms, some of them had property that they were able to make them work in polynomial time. In our case, we don't care about the time complexity of the algorithm, so it can work very, very slow. And we can also say that our algorithms solve this also other variants of this problem. For example, dial and write problem, or the variant with capacity, and so on and so on. However, the technique we use is also the same or very similar to the technique that was used before in the previous results. So some of the previous results also were working very well for these variants. Okay, let's go to the algorithm. The idea of the algorithm is very simple. First, we divide all the time into phases. So the phases start at points 1, 3, 9, and other powers of 3. And every of these points, we will check what optimal algorithm would do for the set of requests that have already appeared. So we will check what optimal solution would do for this group of requests, and we will do the same. Okay, maybe it will not be exactly optimal solution because we just say to him, serve as much requests as you can in this small range of time. So this is the price collecting variant of the optimal solution. However, I will say optimal solution for it. So here we've got some example. Here we've got, we can observe that until the first phase starts, optimal solution is going somewhere. Here is the chart that represents how far is it from the origin at this point in time. And we can observe that algorithm is staying in the origin for this period. And then algorithm is simulating this part, this solution here. And after it's finished the simulation, we have to make the next simulation, we have to go back to the origin. So then we are going back to the origin here. And at this point, we can start new simulation that is here. And we are doing the same for the whole time, going back to the origin. We are looking what optimal solution would do, simulating, and so on and so on. And we are doing it until we will serve all the requests. So let's go to the analysis of this algorithm. Here on this picture, we can observe we have these solutions that I mentioned before. And I will represent the costs of this solution as such rectangles. So this orange, we can imagine this orange part of this rectangle is the cost, or this dark green one here is the cost of this solution. And we can imagine that if higher this rectangle is, then more requests we served. And the length of this rectangle is the length of the phase that it was working on. So this is the picture presentation of these costs. So if we want to bound the cost of our algorithm, we can say that we will pay this cost of this orange solution. However, until we started the simulation, we had a waiting phase, and we were waiting and observing what optimal algorithm will do. So for this phase, we have to pay for the waiting. So the waiting phase is represented by waiting cost is represented by a rectangle that is full. Okay, so we are waiting for all these requests, and then all of them finally gets surfaced. Okay, then we are returning, so there is no additional cost here. However, when we start new simulation of the green solution here, we have to pay this cost for waiting of all these requests here, and similarly for the blue one. So this is bound for the cost of the algorithm. And what can we say about opt? We can observe that if we take long enough period of time, then price collecting variant of optimal solution will finally serve all the requests. So it will be finally, for a very long phase, it will finally serve all the requests, and it will be the optimal solution for all the requests. So for optimal solution, we just need to take the longest simulation here. And this is the cost of optimal solution. Okay, so let's go a little bit further. We can make a small observation. If we take an algorithm, if we take a look into this simulation, we can observe that some of these requests appear also here. So it means that some group of requests that appeared here and some group of requests that appeared here have been serviced by the previous simulation. It means that we can remove this request from this cost. So I hide it under this white rectangle, and algorithm is only paying a part of this green cost and a part of this blue cost here. So this is the bound. In the paper, we called this new request a fresh request. This is green and blue one, and the requests that are under this rectangle are stale requests, so algorithm doesn't pay for them. Okay, how to compare these values? We can observe that they are quite incomparable here, so we cannot do it strictly directly, sorry. However, if we take a part of this solution that finishes at the same point like this one and uses only the same set of requests, then we can observe that, then we can observe that this value is lower than this. Why? Because this is just the cost of the optimal solution for this period of time. So this value will be slower than this one, smaller. And also this value will be smaller than this one. And in the same way, this value will be smaller than this one. So we can make some comparison on parts of these costs. Also, we can observe some simple comparisons, like, for example, if we take this cost of servicing these results, and all of them were serviced after this line, then we can observe that this total cost is bigger than this part, but it is smaller than the whole part, the whole rectangle. So the cost if they would wait until the end of the phase. And we have a set of inequalities, and now we can use them to write linear program. In this linear program, we have all these inequalities, and we are maximizing value of algorithm. However, we make one additional assumption, that cost of the optimal solution is equal to 1. Why can we do it? Because we can scale all the values in our program by the cost of this optimal solution, then this cost is equal to 1. And also, the cost of the algorithm is equal to cost of the algorithm over 1. So it is equal to the cost of the algorithm over cost of the optimal solution. It means that this linear program is maximizing our competitive ratio for this set of inequalities. So in general, this is upper bound for our competitive ratio, because we can put any values here, and if we take any instance, we can put the values from the algorithm into this program, and it will be upper bound. So for now, if there is a possibility to solve this, to find maximal possible value of this algorithm, then we would have the upper bound for this competitive ratio. However, it is not so simple in this case, because this algorithm has some parameters. We don't know what is the number of phases in our algorithm, so we even don't know how big is this linear program in the beginning. If we would know this number of phases, we could just solve it even in polynomial time and find what is the maximal value of this competitive ratio. However, we cannot do it directly. Therefore, we can create dual program. As we can observe, we take our linear program and we create, this is just straightforward, a creation of the dual program. And we can observe that it is minimizing some, objective function. And it has a group of inequalities. It is not very important what these inequalities are. We don't have to understand them. We need to just solve this program at this point. So how to find this universal solution for this program that works for any number of phases? Okay, we can take this program and give it to the human, and he may try to solve it on the paper using just writing the inequalities and trying to figure out what the solution is. But it is not so easy. After some time, we realized that we can use computer to help in finding these solutions. Okay, in using computer, we can take our dual program and check what are the results, what is the objective function, the best objective function, using some specific set of parameters. So we can take any parameters and solve the program. Using computer, we can do also other things like check which inequalities are equalities. It is very helpful in solving such a set of inequalities because now having one value, we can check what is the value of the other variable and so on. So we can also, for example, check what is the numerical solution for different values of parameters of one variable, and then we can try to guess what is we can just look how is this value changing when we change the parameters, and guess what is the formula of this variable. So using computer, we have a very wide range of helpful informations in guessing. However, we need a lot of time to find this solution. But if you just start and go inside this dual program, we did it, and we found some universal solution for any set of parameters that is equal to 4. It means that optimal solution for this dual program is at most 4 because one of solutions is 4. So what can we do now? We can use weak duality. We can take our linear program and compare it with our dual program. And now we know that any solution for this linear program is always smaller than any solution of this program. So we can just take any solution of this program that we found. It's equal to 4. And we know that this is the upper bound for the competitive ratio. So finally, we have proven that competitive ratio of our algorithm is at most 4. And this is the solution for our deterministic case. What about the randomized case? First of all, let's take a look of a difficult example that is very hard for the algorithm to solve. In this example, we've got only one request that appeared. You may observe that it is just a little bit further than the length of the first phase. It means that optimal solution will solve it after the first phase. However, our algorithm will check here what he can do, and he will observe that he is not able to serve anything in this part of time. So he is staying in the origin. Then it is return phase. So it is getting back. So it is still staying in the origin. And now this is the point where the new phase starts and he is able to service this request. So we can observe that it is about 4 times worse than the optimal solution here. And we can also observe that if we would delay our algorithm, if we would be able to delay our algorithm a little bit, he will service this request much earlier. So let's do it. Let's try the algorithm that with some probability makes some delay for the algorithm. And we will, in this case, we will try to make a delay of square root of 3 with probability 1/2. So with probability 1/2, algorithm will service this request at this point, and with probability 1/2, it will service it very late. And that's the idea for our new randomized algorithm. And using the same analysis and using the same dual program, we have proven that this algorithm is 3.36 competitive. So it is already a big improvement. So let's go further. In the previous example, we just divided we divided our algorithm into 2 parts. And what happens if we divide algorithm into m parts, and with probability 1/m, we delay our algorithm with the proper delay. And Using this, once again, the same analysis, the same algorithm, we have proven that the competitive ratio of such algorithm is this. So if we take a very, very big value of m, this value, this competitive ratio is of this randomized algorithm is equal to 2.8. That is our randomized result. Okay, so in the end, I will shortly tell you something about unrelated machine scheduling. I will not introduce this problem because I don't have enough time. However, I want to say that this problem has a lot of properties that are very similar to the TRP. And the most important is that we can try to find some simulation of optimal solution and try to simulate it later after the phase. However, the main difference is that in the unrelated machine scheduling, we don't have to we don't have to go back onto the origin. So after one simulation, we can immediately start new simulation and we don't have the return phase. So we can observe it on the pictures. Here we can observe that we have phases of length 1, 2, 4, and so on. So these are powers of 2. And our algorithm, after one simulation, doesn't have any return phase. It just starts new simulation, and so on and so on. And using this algorithm, we also improved the results for the unrelated machine scheduling. And this we have proven that deterministic upper bound in this case is 3. That is previously it was 4. And we also improved the randomized algorithm for this problem. Okay, so summarizing, in this paper we presented you an algorithm. It's surprising that we presented one algorithm and one analysis that solved TRP and unrelated machines and some similar problems, and it solved also the deterministic case and randomized case at once, and it improved a lot of results. So this is our result. And what are the open questions? Okay, I wrote here the most general open problem that I could. How can we improve it? Or if we are able to improve it? It is a very good question because our idea is that using the same set of phases, for example, 3, 9, and exponential increase with exponential increment, we think that it would be very difficult to improve it. However, maybe some modification, like when we see a very, very big request in the middle of the phase, maybe we can finish it immediately, then go strictly to the origin back, and then try to start new simulation servicing this request earlier. Maybe such a modification would work. However, it is much more difficult to consider. Okay, that's all I wanted to say. Thank you for your attention.